Welcome back, 3C students. Let's use this fun little simulation from the PhET website to demonstrate and discuss, or I guess I'm discussing, a number of basic ideas about traveling waves on strings. PhET stands for Physics Education Technology. So we'll start in pulse mode, and I'll create a little disturbance on the left end of the string. And you can see that the disturbance travels down the string. Now, I'm saying string, but more accurately, it looks like a sequence of particles that are coupled by something like a spring. Since I didn't program this simulation, I don't know the details of the interaction between two adjacent beads. I'll call them beads or particles. But it's probably something like little springs in between each pair. So you'll notice that the amplitude or the height of that disturbance decays a little bit as it travels to the right. You see that? It's getting a little shorter on its way through the window. And that's because of the presence of damping, which is basically friction. So if I put the damping to 0, you can see that the amplitude of that bump stays constant. And there's no loss of energy there. One important first observation about waves on a string, and for that matter, any wave that requires a medium, like sound waves require air particles as their medium, water waves pass through water. One of the important points about those waves is that the matter itself does not get transported from one place to another. All of these beads are in the same position that they were in before the pulse passed through them. So it's not matter that's traveling in a wave. Rather, it's energy itself. That may not be obvious. What you see directly is the disturbance that's traveling, but there's energy associated with that disturbance. And watch what happens to the speed at which that pulse travels if I decrease the tension. You all have some sense of what it means to discuss the tension in the string. If you pulled it harder between two fixed points, you would have increased the tension. So if I put the tension down near the low end, you can see that the pulse travels much more slowly. And a lot of you probably have direct experience with this. If you spent any time playing with jump ropes as a kid, you hold one end, your friend holds the other end, and you know that if you oscillate one end up and down, you can see the pulses travel down the string. And you probably noticed that if you pull the string, or the rope, I should say, tighter, then those pulses travel more quickly. The same thing is true for guitar strings, although those pulses travel so quickly, you've probably never noticed them. Okay, so tension has an obvious effect on the speed at which a disturbance travels down the string. Now, I mentioned just a moment ago that the height of the pulse stays constant. You could say it's preserved if there's no damping. What else stays constant? How about the pulse width? So I will increase the pulse width, and that means that this rod is going to take longer to complete its disturbance of the left end of the string. And you'll see that as a result, the overall disturbance has a greater width. Not a huge difference there. And that width also stays the same. So it's kind of remarkable that the shape of the pulse is also preserved. Let me just go to manual here and make an arbitrary shaped pulse. And you can see that that shape is preserved. Most of the time in this chapter and subsequent chapters, we're talking specifically about sinusoidal waves, but it's important to keep in mind that any type of disturbance could be transmitted through the medium and preserve its shape. And I said a moment ago that you can think of each adjacent pair of particles as having like a little spring between them. Whatever the nature of their interaction is, these are definitely all coupled oscillators. I say oscillators because they're free to move up and down. Just focus your attention on any of these beads, like this green one right around here. It's clearly oscillating up and down. Now, why is it oscillating when it's not being driven directly by this rod over here? The rod on the left end can only directly influence this green bead at the end because that's the one it's touching. It's not actually touching these other beads. So each of these beads is being forced to oscillate by the beads adjacent to it. That's the coupling. In a previous video, I showed you just two oscillators or two masses bouncing around on springs and coupled by a third spring between them. And the motion of one produced motion in the other. That's what we're looking at here. Just it's more complicated because we have a much greater number of beads, or of oscillators, I should say. What next can we say here? Let's go to, let's talk very briefly about boundary conditions. If I choose a fixed end, so now the bead on the right is no longer free to move. Let me just make a single pulse and watch what happens to the pulse when it gets to the end. See how it went from the top side to the bottom side? It was inverted. And it's kind of easy to understand why intuitively, but you want to remember that behavior because later we're going to pay much more attention to light waves than waves on strings. This is really, talking about waves on strings is really just a good way to get familiar with wave behavior and wave vocabulary before we talk about the more interesting case of electromagnetic waves. And we'll see that electromagnetic waves can also be inverted, so to speak, when they're passing from one medium to another. It's a different type of boundary condition, but the behavior of the wave is the same. Now, if we change the boundary condition, if we allow the bead on the right end to move freely, now watch what happens to that pulse. And I'll increase the tension a bit here. Oops, restart, please. Okay, so instead of being fixed at the end, it's just attached to this ring, which is free to slide up and down that rod at the right, and there's no inversion upon reflection. Again, there's an analogous case when it comes to electromagnetic waves. So later in the semester, we'll talk about the circumstances which produce an inversion or not an inversion of an electromagnetic wave when it reflects. For instance, if light is traveling through air and it reflects off of glass, there's typically an inversion of the electric field. Okay, so I mentioned that what you're really looking at is the traveling of energy down the string. Now, in the previous video, I reviewed simple harmonic motion. If I put this thing into sinusoidal oscillation, it's very clear. Ooh, we need some damping here because this is getting crazy. It's very clear that each of these beads is executing some kind of simple harmonic motion. And we also saw that if you quantify the energy of an individual bead, it depends on the square of the amplitude of the oscillation. So if I just make a pulse here, let's see here. Okay. I don't want any damping. One more time, I'll get this right. Okay, I'll pause in the middle there. These beads over here have no energy because they're not oscillating, or you could say that their amplitude is 0. This bead in the middle here has more energy than any other bead because it's currently oscillating with the largest amplitude. So each of these beads, which can be regarded as a simple harmonic oscillator, passes its energy on to the next one as the pulse travels by. And once they've given up that energy and the string settles in here, the energy is no longer in that location, it's somewhere else. So it is helpful to think about a wave on a string as a long sequence of harmonic oscillators, which are receiving energy from the previous one and then giving it up to the next one. And that also makes, when you think about it in those terms, it also makes it easier to understand how the greater the height or the amplitude of the wave, the greater the rate at which energy is being passed down the string. If I make a larger amplitude pulse, can I do that? Yeah, I'll do that down here. Let me just pick an easy number. Since we're familiar with the joule as the unit of energy in the SI system, let's say that right now, each of these beads receives 2 joules of energy from the previous bead as the pulse passes through. Whereas before, with the smaller amplitude pulse, maybe this represents only 1 joule being passed from each oscillator to the next. Well, if it takes 1 second for that pulse to travel from the left to the right, then in the case of the high amplitude pulse, that's 2 joules of energy flowing down the string in 1 second. 2 joules per second, that would be 2 watts. Whereas previously, if only 1 joule of energy is passed from left to right during that time of 1 second, that's only 1 joule per second or 1 watt. So these are silly numbers I'm picking, but hopefully that makes it clear that the amplitude of the pulse determines how quickly or the rate at which energy is passed down the string. And we have a word for that. Just now I was using the units of watts. That is the unit of power in the SI system. So the power along a wave, or the power flowing down a wave, I really should say energy flowing down the wave or the string, because power is the rate at which energy flows. But if we want to be a little sloppy, we can say that the power flowing down the string depends on the amplitude. Specifically, it's on the square of the amplitude. Okay, let's go back to the oscillate mode. And we need a little bit of damping so it doesn't get too wild. And let's look at how the wavelength depends on the tension in the string. So if I put the tension all the way up to the high end, and there's actually not a very well-defined wavelength here. Later, we're going to look at standing waves. But if I pause it, loosely speaking, the distance from this peak to the next peak is the wavelength. And you can see it's much longer than it was when I had the tension down low. So what's up with that? Well, if we go back to the pulse mode, when the tension is high, the speed of the disturbance is also high. So with the tension set to the high end down here, if I give the left end of the string a little shake, you can see that that pulse travels fairly quickly through the string. On the other hand, with low tension, we have, as a result, a much slower speed. The pulse takes longer. And that should help you understand why, if instead of a single pulse, you're driving the left end of the string repeatedly, in other words, you're forcing it to oscillate, then at low tension, each pulse that you make isn't going to go very far during the time until your next shake, right? Between shakes, each pulse doesn't travel very far because the wave speed is low, and that's because the tension is low. On the other hand, let me reset. If we put the tension up high, and now each individual pulse again travels more quickly. So if I go back to oscillate now in between shakes of the driver here, because each pulse travels more quickly down the string, it's going to travel farther in between shakes. So by the time you make your second pulse, the first pulse has already traveled a significant distance down the string. And as a result, the distance between each pulse is greater. In other words, the wavelength is greater. So if you get that, that's going to help you a lot with our further investigations of waves. So for a given frequency, I didn't mean to introduce that term right now, but for a given frequency of shaking, the faster the wave travels, the longer the wavelength, because each pulse goes farther before you make the next pulse. But since we're on that topic, let's leave the tension up high, which means the wave speed is high. And now what we can alter is the frequency. So down here, I can make this driver shake the string faster. And you see how the wavelength has now gotten shorter. The distance between subsequent pulses is less than it was before. So the pulses are still traveling as fast as they were before. I didn't change the tension. They're still traveling the same speed, but they don't have, they can't go as far between shakes because my shakes are happening more often. So I guess we've just discovered 2 ways to decrease the wavelength meaning the distance between each pulse. You could either shake the string faster, that means raise the frequency, or for a fixed frequency, you could lower the wave speed. Remember, when the tension was low, the speed was low, the pulses didn't travel as far in between shakes. And the last thing I think I'll talk about with this simulation, before I bore you to death with this one screen here, is the accumulation of energy on this string. So let me go back to a fixed end with no damping. You kind of saw this a few minutes ago. Oh, too crazy. Restart. Okay, let's go with a medium frequency. I'll pause for a moment. Now, when you first start to shake the string, you've got energy flowing to the right. When it hits the right end, because of that boundary condition, the fixed end, the energy has to reflect. It can't go through the window like previously. So that energy is going to bounce backwards. And then to some extent, it's going to be reflected again when it hits the driver. So the energy is just bouncing back and forth. It can't escape the system necessarily because I've put the damping down to 0. So there's no friction. Well, I'll just call it friction. There's no friction within the string that's able to dissipate the energy that I put into the system. Now, it is possible to remove the energy by doing work on the system, just like if a car is rolling down the street at 2 miles an hour, it's possible to push backwards on it and slow it down. And so the driver here could actually be doing negative work on the string. If these beads were moving downward while the driver was moving upward, that would be negative work that's being done, and you could take energy out of the system that way. But if this driver is always doing positive work, then it's always putting energy back into the system, or more energy into the system, and there's no way for the energy to escape. So you would expect the total energy within the system to just keep increasing and increasing. And that's what you're seeing here. Do you see that the amplitude is now large enough that it's off the screen? We know that total energy is proportional to the square of the amplitude for harmonic oscillators. Let me try this again with an even lower driving amplitude. And we'll see that after several seconds, the total amplitude just keeps increasing and increasing. Now, in real life, let's think about this. Suppose this wave represented the oscillations of air inside a musical instrument. So the driver here, let's talk about a trumpet, because I'm familiar with trumpets. The driver could be like the trumpet player's lips buzzing inside the mouthpiece. They're the one putting energy into the system. And these oscillations, we'll talk more about this, but this sine curve could represent the oscillations of air inside the trumpet itself, the tube. And the whole point of a trumpet is to put energy into the outside universe. So that would be like damping, except instead of friction, the oscillating air inside the trumpet is losing energy by sending out sound waves in all directions away from the trumpet. But in order to produce a tone on the trumpet of constant volume, of course, the person playing the trumpet has to keep putting energy in at the same rate that it's leaving. Otherwise, the sound would get, it's like if you hit a bell with a mallet, the ringing of the bell is loud at first, and then it decays over time because you only put the energy in once at the very beginning. If you want it to keep ringing, you'd have to keep striking it in order to reach that equilibrium. Now, if you found it a little difficult to believe based on that simulation that a disturbance created at the left end would travel down the string unaltered in shape, like the triangle-shaped pulse that traveled down the wave or down the string, here's a really nice video that should convince you that that really is the way waves or disturbances on strings can behave. So this guy, Bruce Yeany, has a ton of great content. He's linked several times on Canvas. Check out his YouTube channel sometime. I believe he was a high school teacher, but he made some of the best demos I've ever seen for physics classrooms.
Hello, I'm Bruce Transverse Yeany, and today we're going to take a look at some slow-moving waves. Now these are going to appear on a piece of moving string or rope, but let's start off by taking a look at some waves traveling through stationary rope.
To make waves in rope, it's as simple as flicking it up and down or side to side. We could also use a slinky.
Wow, Homework's good at that.
Now what we're looking at is a transverse wave. The material is going to stay stationary. The particles of the material move up and down as the wave moves forward through it. That is a transverse wave. So, ready?
Yeah.
Now,
Go. Begin.
yeah. Bring it back.
Bring it back.
All right, let's try again. Ready?
Yeah.
Really fast?
Yeah.
Now what we want to do is put this rope in motion. The rope is going to go in this direction. We're going to move the particles of the rope to form a wave moving this way, but it's going to go against the movement of that rope. So that's going to cause this wave to slow down. Now we're going to look at it on a vertical rather than a horizontal.
Let's start by taking a look at the device. It's simply a spool that's mounted on a toy car wheel. Here we can see the wheel a little bit closer. This is going to mount on the motor, which is mounted inside the wooden support. It has wires that run down to the base. Here's the on-off switch. And if I turn it over, there we can see the batteries.
Now here's my continuous loop of ribbon. When I put it on this wheel, I can move it back and forth, and it hangs very limp. There's not much to it. But when I turn this on, this wheel is going to turn in this direction fairly quickly. So this whole ribbon is turning in this direction. It's coming up on this side. So if I pull this out and put a weight into it, you see it propagate down this side very slowly.
So if we want to be fancy and use the vocabulary that you've acquired in these classes, 3A, 3B, 3C, we would say that we've actually placed ourselves in the reference frame of the moving pulse. If you want to think about it in terms of relative velocities, if this string were, or it's really a ribbon, if it were pulled taut without, rotating over this wheel, and he were to pluck it, you could expect a pulse to travel very quickly down the ribbon, but he simultaneously has the medium or the ribbon itself moving upward. So those two velocities cancel, so to speak, and that's why you can almost watch that pulse just stationary in space. It has a very small velocity downwards.
This is the side where the ribbon's moving down. So if I try and put a wave on this side, well, I can't do it. It almost acts like it's a rigid body. Behaves much differently.
Okay, here's another guy explaining the difference between transverse and longitudinal waves, both of which will be important in the next 2 chapters.
Hi guys, today I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy is going to go this way. But with a transverse wave, the medium, so in our case the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go. So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now, another kind of wave is a longitudinal wave. Now, with a longitudinal wave, the medium, again, which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction. Our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave. So in this case, you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied, and that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay.
More than once this semester, we'll be looking at materials posted by Dr. Dan Russell, who's got some awesome simulations here of various wave phenomena. So let's look at a real simple, well, I say simple, but I wouldn't know how to program this, animation of longitudinal waves, or as that British guy in the video said, longitudinal. I think normally we say longitudinal. And the first thing I'm observing is that it's almost like an optical illusion. When you first glance at this top simulation, it gives you the impression that there's bulk motion of the matter from left to right. It looks like, like there's a column of atoms here that's actually traveling from one end of the tube all the way to the other, but that's really not the case. And you can see that if you focus just on this dot that's been highlighted in red. Do you see how it's really just oscillating back and forth about an equilibrium position, much like a simple harmonic oscillator? It's a lot like a mass just connected to an ideal Hooke's law spring. And so you can anticipate that the motion is sinusoidal or close to sinusoidal. And it's not just that red dot for which that's true. Pick any of the dots here, train your vision on that dot, and you'll see that it's really not moving down the tube. It's just oscillating left and right. Now, what is traveling down the tube is this region where the particles are more dense, and that's called a compression. You saw that in the Slinky video. So you've got these regions of greater pressure, a lot like in the FET simulation, a lot like the peaks of those sinusoidal oscillations. Each peak travels down. I was calling it a pulse. Each pulse travels down the string. Here, the pulses look like these compressions. In between the compressions, we call those regions rarefactions. In the previous video, the Slinky guy said that the Slinky was rarefied in between compressions. So we'll make more sense out of this soon. There's some great diagrams in your book that help you understand how this phenomenon results from a sinusoidal longitudinal oscillation of these, I'll call them air particles. Here's a little simulation of transverse waves. And even with these transverse waves, you almost get the impression that there's bulk motion of matter from left to right, not as much as with the longitudinal waves, but it's pretty obvious that each of these particles is merely oscillating up and down. So there is the difference between longitudinal and transverse waves. In both of these waves, the energy flows from left to right, but for transverse waves, the particles are oscillating up and down. That's perpendicular or transverse to the direction of the energy travel. Whereas with longitudinal waves, the particles oscillate left and right, which is parallel to the motion of the energy. And we'll be concerned with both types of waves. Sound waves would be the most familiar example of longitudinal waves, although that's not obvious that they're longitudinal waves. And then the most important transverse wave that we look at will be the electromagnetic waves. And you may be wondering, what exactly is waving in an electromagnetic wave, which is what light is. And of course, it's in the name. It's the electric and magnetic fields which are waving. So you don't want to be misled by these first two examples into thinking that all waves involve strictly longitudinal or strictly transverse oscillations. Evidently, water waves involve simultaneous oscillation along both axes. Now, I've never studied this branch of physics in any depth, but evidently it's known that in water waves, the particles move in circles. And I think they even tell you, no, that's the next one. If I go down here to Rayleigh surface waves, these are evidently the waves that you feel the most during an earthquake. Look at how this particle on the surface is moving counterclockwise around an elliptical path. But if you go down far enough, it switches from counterclockwise to clockwise. And it's even been calculated the depth at which it switches. So particles at a depth of more than 1/5 of a wavelength trace out clockwise ellipses. That's peculiar behavior. I don't know how to explain that. You probably have to take a class in acoustics or maybe even fluid dynamics to see the explanation for why that's the case. So we're not going to do that in this class, but we will use math to show a number of interesting results about longitudinal and transverse waves. Here's a screenshot of the simulation. Focus your attention again on the red particle. And I've drawn this vertical blue line to represent the equilibrium position of that red dot. So if there were no disturbance propagating down this medium, and in this case, it's a sinusoidal periodic disturbance, in the absence of that disturbance, that red particle would just be hanging out on top of the blue line. That's its equilibrium position, just like when you have a mass on a spring and the spring is neither stretched nor compressed. Well, a moment later, let me back up for a second. So let's use the same notation that your book uses, and we'll speak of the displacement of that red dot from its equilibrium location. We will use capital D for displacement, and it depends on two variables. And I really need to grab my laser pointer. The displacement function that we use when we talk about waves in the first month of this semester here depends on two variables. X, which is really your position along the medium, and time. And for now, think of X as really like an index that labels which particle you're talking about. Are we talking about the displacement of a particle over here, like this red one, or the displacement of the particle that normally hangs out right here? So X is a coordinate. It's kind of like an index that refers to this particular position in the medium. Now, what complicates things here is there's a whole bunch of particles that actually hang out on this blue line. Let's just look at all the particles along this line that I'm indicating with the laser pointer. So X is a variable that allows you to choose a particular particle to talk about. So the displacement at a particular value of X and at a particular value of time depends on those two variables. Right now, since the particle is to the right of the blue line, we consider the displacement to be positive. It's a number greater than 0. A moment later, your particle will have moved to the other side of the equilibrium position. Now its displacement is some negative number, some number less than 0. So if you go back to the simulation and hit play and watch that particle bounce back and forth or oscillate, its displacement goes positive, then negative, then positive. Again, a lot like sine and cosine. Don't forget, though, that while the particles don't actually flow down the tube, they're just oscillating about a single position. There is energy flowing down the medium. Transverse waves. Remember from the simulation, these particles were jiggling up and down. So now let's consider, it's like I've tilted my x-axis on the side. The x-axis goes up like this. No, that's not correct. I just misspoke. X is still a variable that tells you where you are in this direction. Like, let's just go with this line cutting through the medium right here. Different values of X correspond to different particles. Again, it's like an index that tells you which particle you're talking about. The displacement now, the displacement axis, if you want to call it that, is vertical. So positive displacements will correspond to the particle being above its equilibrium position. So again, let the blue line represent the equilibrium position of this particle. Sometimes it's above the line, sometimes it's below. Oops. So a moment later, now it's below. and you can consider that a negative displacement. So the direction of the displacement is perpendicular to the direction of energy flow. That's what we call a transverse wave. So you can see there, oscillations are this way, energy flow is this way. Those are perpendicular. That's characteristic of a transverse wave. So now let's figure out how to describe these one-dimensional waves mathematically. And we'll start with the simple translation of a function. And of course, we're not talking about translating from English to French. Translation in this context means really just scooting the function left or right. So take a look at the orange curve, which I've decided to call G. G of x is that orange curve. And you'll notice that it's identical to the blue curve, which I'm calling f of x, except for the fact that it's been scooted to the right by a 1, a 2, a 3, 4 units. So the height of the orange curve, that's g, at x equals 5, that height evidently is the same as the height of the blue curve at x equals 1. So the height of g at 5, x equals 5, is the same as the height of f at x equals 1. Here's how we state that with the function notation that you've been familiar with for years. We say the function g evaluated at 5, of course that's short for x equals 5, equals the function f evaluated at 1. Remember, graphically, the height of the curve is the value of the function. You plug in an x coordinate, that's a number. What you get out is another number that you use to be the height of the curve. So g of 5 equals f of 1. And we could also write that as g of 5 equals f of 5 minus 4. So the height of curve g at 5 is the same as what you get if you look at the height of curve f, not at 5, but at 5 and then back up by 4. And that's true everywhere on the x-axis. So if I pick a different x-coordinate, how about 2.5, the height of the curve g at x equals 2.5 is right here. That's the height. And you can see that that's the same as the height over here of the blue curve at x equals negative 1.5, which is 4 to the left. So the height of g at 2.5 is the same as the height of f, 4 to the left, at x equals negative 1.5. Same statement as before, but now I'm relating two different coordinates. So in general, you could pick any arbitrary place on the x-axis. Here's a particular location with coordinate x. The height of the curve g at x is the same as the height of the curve f at x minus 4. Hopefully this is familiar to you. You may have dealt with what they call parent functions, I think, in algebra. I learned this in algebra 2 years ago. And let's look at the same thing more interactively in Excel. Full disclosure, I've turned into a bit of an Excel nerd, spreadsheet nerd. This isn't the first time, well, no, this isn't the last time this semester that you'll see me make use of Excel. It's a much more versatile program than I realized. It allows you to do some programming without a lot of programming, if that makes sense. Not a whole lot of syntax. We are going to use Python this semester, but Excel's intuitive and you get to see everything in real time update in these spreadsheet cells. Okay, so we're looking at the same two curves here. If you're curious what the definition of this function is, there it is, sine of x over x. If you take the sine of a number and divide by that number, that's actually called the sync function, S-Y-N-C, and it's going to play an important role in our study later of the diffraction of light through a slit. So much more on that later. It's like a sine function whose amplitude decreases as you move away from the origin. Now, don't worry about the details here. This is really just a column of x coordinates and a column of corresponding y coordinates for the blue function f, and then a column of corresponding y coordinates for the orange function g. And if you look at the syntax here, I'm really taking the sine of x minus cell B1, which I've labeled with the letter H. So that's the amount by which I'm going to scoot the function to the right. Now, I should have pointed this out already. It may be a little counterintuitive that a minus sign appears here, even though the function g, the orange one, is being scooted to the right. If you subtract a number in the argument, you actually scoot the function to the right. And the way Excel works, because I'm always making this absolute cell reference to cell B1, see the dollar signs there? I can change whatever number's in that cell, and it will automatically update all these coordinates, which will also automatically update the graph. That's a nice feature of Excel. So if I change this to 2, did you notice that all of these y coordinates for the orange function automatically updated, and that was reflected in the graph? So right now I'm calling the amount of scoot h. That's the amount by which I'm translating the orange curve. And as I increase h, I scoot my function more and more to the right. So right now, h is 7. And I'm just doing this verbally, but if you look down here at the legend, the orange curve g of x is really f of x minus 7. So the height of the curve at 7, the height of the orange curve at 7, is the same as the height of the blue curve at 7 minus 7, which of course is 0. That's it. Hopefully this is sinking in already. At any place along the orange function, if you'd like to know the height of the orange function, it's defined in terms of the blue function. It's the same as the height of the blue function if you scoot to the left by h units. That's it. That's how we translate a function. Okay, now think back to the pulses that we looked at in the PhET simulation. Suppose a pulse began at the left side of the string and it had this shape, the sinc function. And as time goes on, we know that that pulse will propagate or travel down the string to the right at speed v. Now suppose a certain number of seconds has passed. We'll call that time t. And you remember from 3A, hopefully, or just common sense, if something has been moving at a speed v for t seconds, then vt is the distance it has traveled, right? Distance equals velocity times time. So since we know the amount by which the pulse has been translated, we can use what we've just learned to express that mathematically. So the height of the orange curve, which represents the pulse at the time t, you can get the height anywhere on that curve by just equating it to the height of the blue curve if you scoot back to the left by an amount vt. Same thing we've been doing, but now instead of calling this quantity h, that distance can now be expressed as the product of velocity times time. Does that make sense? Why am I asking you, right? You're not gonna answer me unless you shoot me an email and say, hey, I'm really confused. And that's going to be true at any time. So if this is true at time t, then half a second later, I don't have a graphic, but half a second later, this pulse will be even farther to the right, which means the quantity vt is even bigger, and we would have to plug a different number in here. So the idea is, as time advances, t advances, this quantity gets bigger. So we're subtracting a larger quantity from x. That means we keep translating mathematically this function farther and farther to the right. Now that takes some imagination, unless, of course, you've got an animation or a cool website that allows you to witness that directly. So here we are at the super cool and best of all free website, desmos.com, for their graphing calculator. Now you could be lame and type this URL in directly, or just Google Desmos graphing calculator. Just GTS to use the parlance of our times. So as a simple example here, what if we ask them to plot, oh, okay, sure, let's go with that, y equals x. You don't actually have to type the y equals, it's implicit. X is fine. Now, if you try a different variable, like if you'd like to plot something versus time and you call it t, it won't know what to do with that. So unfortunately, you are stuck using x for your abscissa. That's the old-fashioned word for the horizontal coordinate. So if I ask for the graph of sine, as expected, how about e to the x? Does that work? Ooh. You could also say exp a lot of times, or that's an older notation used in a lot of books. What about the square root of x? Oops, capital X. Yeah, okay, that works. So it's all pretty intuitive. I'm going to stick with the sinc function that I've been using. So sine of x divided by x. All right. And since it's not tall enough, I'll stick an amplitude out front, or change the amplitude. That looks good. And we would like to make this thing scoot back and forth so we don't have to use our imaginations, because that's exhausting. Remember how to do it. If you want to translate a function to the right, you must replace x with the quantity x minus h, where h is a parameter. And that's everywhere, so not just inside the sine function. I have to do it down here as well. And what's cool about Desmos, the graphing calculator, if you use any variable other than x, it will automatically assume that that's some sort of parameter. So it's making the assumption that h is a parameter and giving me the option of adding a slider so that I can control h. So right now, h has the default value 1, so we're really evaluating the sine of x minus 1 divided by x minus 1. And as we saw earlier, that's going to take the sinc function and translate it to the right by 1 unit, as you can see here. Now, if I drag the slider to the right, increasing the value of h, sure enough, the function gets scooted farther and farther to the right. So we no longer have to use our imaginations. We can easily manipulate this graph here in the calculator. Now, even cooler than that is we can even animate this. So instead of doing it in terms of h, let me actually enter now velocity times time, velocity times time. So if you want to be consistent, pardon me, if you want to be consistent with the previous notation that I was using, our parent function, the base function that we started with, I called it f of x. So here our f of x is sine of x over x. And we're going to turn that into f of x minus vt. So everywhere there was previously an x, I have replaced it with the quantity x minus vt. And now it's giving me the option to add sliders for both of those variables. So let's leave the speed at its default value of 1. And check this out. Let me drag the slider for time all the way back to -10. I'm going to hit play, and that will cause the value of t to range from -10 to 10. Now, as t increases, so does vt. That means we're subtracting a larger and larger quantity from x. Here I go. Beautiful. As expected, as time advances, our wave or disturbance, whatever you'd like to call it, it travels to the right. And why don't you observe this, the speed of that motion? You know, I have a lingering cough because I actually did have COVID. For me, it wasn't bad. And I should point out that some of the future videos that you'll be watching this semester were recorded last year, spring 2020, right after COVID hit. And it didn't seem real serious at the time, so I made a couple stupid jokes after coughing about having COVID. Well, I actually did get COVID, and now I have that lingering cough. So please just ignore it. Observe the speed at which this pulse moves to the right. And what happens if we change the value of v? Let's put v up at like 5 times its original value. What do you expect to see now when I hit play? What did I just do? When I hit play for the t parameter. I'm trying to give you a good view here. Here I go. It's probably difficult to tell because I accidentally zoomed out, but hopefully it's evident that, here, let me go back and repeat that with a slow speed. What's happening? Why is this thing going to the left? This is confusing. V minus x minus vt over x minus vt. Oh, right, because I was supposed to hit play on t. Okay. So that's the pulse moving with the speed of 8.11. Let's rewind the clock, and this time put the speed much lower, and sure enough, it does not move as quickly. So hopefully you're convinced that this quantity v really is a speed. Now this next step I'm going to do is a little silly. It's a little whimsical and not necessary for what's coming in the chapter, but we could even modulate the amplitude of this function by sticking out front something like 5, let's go with 5 times the cosine of t. So as t increases, let me go with even 20. Yeah. As t increases, remember, cosine actually dives down as t increases from 0, right? Sine is the one that starts at 0 and increases. Cosine starts at 1 and then decreases. So as time goes on, this cosine function here is going to move towards 0, and that should actually change the amplitude. Okay. I guess it's oscillating a little too quickly. Let me put something like 0.1 in front there. Then I'll try that again. So that's kind of cool. You can see how the height is also changing in time. I'm just giving you a flavor for the things you can do fairly easily with a graphing application such as this. Let's do one more thing before we leave the Desmos site here. I've made one small change. You see I changed the minus sign to a plus sign. Any guesses what that's going to do to the motion here? Well, rather than me just pausing with my speech here, you can pause it in your browser and think about it. Let's start time at -10 seconds. Hit play. Aha. So if we replace the minus sign with the plus sign, we have now mathematically represented a disturbance that travels the opposite direction. So you just want to memorize that. Minus sign, the pulse travels to the right. Plus sign, the pulse travels to the left. And if you want to convince yourself of why that works, just review the argument we made in this video for pulses traveling to the right, and you should be able to see why that works. Now here's another very useful observation. I've picked an even stranger looking arbitrary curve, f of x, and right now f of x is not a moving waveform. It's just a fixed curve in the xy plane where the y coordinate is the height, or I should say the value of the function. And let's look at a particular point on this function. At the x-coordinate 7, the height is, and I'm just picking these numbers, let's suppose this is 7 on the x-axis, and that the value of the function there happens to be 5.3. So whatever this weird function is, and obviously you can't express it in terms of e to the x, sine of the x, or sine of x, x squared. None of the familiar functions look like that, but that doesn't matter. The point is that when you plug the number 7 into those parentheses, in other words, when 7 is the argument of the function, the output is the number 5.3. Now, if we'd like to set this wave in motion and have it move to the right, what do? Well, we've just been discussing that. Replace x by the quantity x minus vt. And now, as time advances, this entire waveform will translate to the right at speed v. And suppose we'd like to track the motion of this particular point that we already looked at. This point that was previously associated with the x-coordinate 7 and has a height of 5.3. Let's see if we can track the motion of that point. And we know that that height results, 5.3, is the output of the function if you plug in the number 7. So this entire expression, x minus vt, regardless of what x is, what v is, and what t is, the combination x minus vt needs to be the number 7. in order for 5.3 to come out. Now, technically, you'll notice if we go over, there are other points in the function that have the same height. Forget about that. We're just looking at this particular location on the curve that has a height of, did I say 7? I meant a height of 5.3. Okay, so the combination x minus vt overall needs to equal the number 7. That way, when you plug in that entire argument, what pops out is 5.3. So look at this condition. As time advances, x minus vt must always remain equal to the quantity 7 if you're talking about the particular x coordinate at which the height of the curve is 5.3. Remember, the idea now is this whole thing is in motion. So when we started the clock at t equals 0, this point was above the x coordinate 7. But as time goes on, this whole thing moves to the right, and this point will be above some other x coordinate, and then some other x coordinate. Well, what's the relationship that x coordinate has with time? Obviously, as time increases, this x coordinate also has to increase so that their difference is always equal to 7. Let me repeat that. As time advances, we're subtracting a larger quantity. That means this quantity, x, must also be larger so that their combination is still equal to 7, so that when we plug that into f, we still get the height 5.3. Solve this for x, and you get a familiar looking equation, because you've all taken mechanics. You all remember your constant acceleration kinematic equations. This is the equation that describes the one-dimensional motion of a particle moving at constant speed v. And this would happen to be its initial value. There it is. So this equation right there hopefully makes it obvious that the location, the x-coordinate below this point, as this entire wave travels to the right, the location of that point on the x-axis is increasing with time, and it's given by x equals vt plus the initial value. All right? So hopefully this convinces you that this quantity v really is the speed. Anything else we can say about this? No, time to move on. Okay, now I'm going to get a little bit more mathematical. And what I'm about to talk about is in your chapter. You may not have used partial derivatives a whole lot at this point in your academic career, but they're really nothing to be intimidated by. They're really no different from an ordinary derivative conceptually. So, at a particular location on the x-axis, suppose we're watching this waveform translate to the right, and we'd like to know how the value of f changes with time. So let me go back so you have something concrete to think about. Yeah, this works. Let's pick, fine, x equals 7. Well, the height of the curve right now, I chose the number 5.3. When you put this entire waveform in motion to the right, then the height of the curve at this position is going to change, right? Won't it start to dip down because we'll be tracing this out? That's kind of confusing. This waveform is actually moving to the right, and that means that the height of the red dot is going to do this, excuse me, as it moves along that curve. So we would like to express the change in the height of the function right here with respect to the change in time. If time increases by a little bit, what's the corresponding change in f? Well, obviously, delta f is going to be a negative number at this point because the height of the function is decreasing as this thing moves to the right. So let's express that using the calculus. And in order to do that, I have to introduce another variable. This garbage right here, x minus, garbage is my word for stuff. X minus vt, yeah, that's 3 quantities combined. Let's just call it one quantity. Like after you plug in x and plug in v and plug in t, you get one number. I'm going to call that number u. And that number really is the argument of the function, right? The argument is the overall number, the input to the function f. If we'd like to know how f changes with respect to t, and this is our first look at a partial derivative here in 3C. This fancy script D is exactly that. It's just df dt. That's how you would say it. But we use the script D instead of the regular D because we're acknowledging that f actually depends on two variables. If you change the location on the x-axis, you're going to change the height of the function. And if you change the time at which you're evaluating the function, you will also change the height of the function. So it's possible to ask how f changes with respect to x or t. Right now we're saying, okay, let's look at a particular x value, like 7. Don't change x, just ask at x equals 7, how does f change as time changes? And if you think about it, the height of the curve is just going to go up and down if you're talking about a sine wave. Okay, well, what I've done here is use the chain rule. I've invoked the chain rule for a function of two variables. Remember, we think of v really as just a constant. The speed is a constant. So in order to take the rate of change of f with respect to t, we first have to take the rate of change of f with respect to everything inside, and then take the rate of change of everything inside with respect to t, right? Let's work backwards. If t changes, u changes, right? Changing t changes this entire number, x minus vt. And if you change the entire number that you plugged into f, then obviously you're going to change the output of f. So any changes in t kind of propagate backwards to a change in f. If you change t, then u changes, and if you change u, f changes. So this notation here, the primed notation, really just means df du. It's the change in f compared to the change in u. So maybe a more familiar way to write that would be this. And I'm just using the chain rule here. F depends on t through the intermediary of u. So the chain rule says if you want the change in f compared to the change in t, first get the change in f compared to the change in u, which is the whole number inside, and then multiply that by the change in u compared to the change in t. And this notation's nice because you can see directly how the delta u's cancel. I almost said cancel essentially. I try not to abuse the word essentially. So if you let the du's cancel in your mind, you're left with df over dt, which is exactly what we want. Okay, so this is the chain rule for a function of two variables. You don't have to totally get this to do well in this class, trust me. So don't stress about that. It would be nice if you understood it because other things will seem easier to you. Okay, so I'll go back to the f prime notation instead of df du. And then what is the partial of u with respect to t? Excuse me. Well, that's easy to calculate. Here's the definition of u, and here's how you do a partial derivative. If you're just asking how u changes when t changes, then you treat t as the variable and you pretend that x is constant. Remember a moment ago I said, let's just park ourselves at a particular x coordinate like 7 on the graph and ask how is the height of the curve changing there with respect to time. So we're not moving position, we're just allowing time to change. So if you're doing the partial of u with respect to t, then regard x as merely a number like 4 or 13. It doesn't matter what number. You know what to do with numbers when you take derivatives. You just ignore them, right? They just go away. The derivative of a constant is 0. So if you take the derivative of this whole thing with respect to t, well, d dt of t to the first power is just 1, and we're left with the negative v out front. Hopefully that's elementary for you. So the partial derivative of u with respect to t is negative v. Let's take this and plug it in here. And I know some of you, your brain's starting to get tired, so just hit pause and come back to this. This is definitely, we're already getting into something a little more mathematical than what we do most of the time in this class. Okay, so I've now determined the first derivative of the height of the curve with respect to time. And it's this expression. What do we do with that? Well, you'll see where I'm going with this. I'm working my way towards a very famous and widely used equation that comes up all over the place in physics and engineering. It's called the wave equation. And we're trying to establish the terms on both sides of that equation. So now we need, you'll see, we need the second derivative of f with respect to t. Now I really, I should have a graphic of this, but the second derivative of f with respect to t. F is the height of the curve, right? So the derivative of the height with respect to t is really the velocity, the up and down velocity of that point, and the second derivative of the height of the curve with respect to time, pardon me, would actually be the acceleration of the up and down motion of that point on the curve. Okay. So in order to take the second derivative, well, I've repeated the information that we've already determined down here. The second derivative is the derivative of the derivative. So let's take the time derivative of df dt, and we've already determined that this is df dt. Okay, now what do? Well, v is a constant, that's trivial. F prime of u is a function that has u in it, and remember, u contains t. So there's a t contained in here implicitly. That's really what we're differentiating with respect to. So we will invoke the chain rule again. If we want the derivative with respect to t, let's first ask, how does all of this stuff change with respect to u, and then multiply by the derivative of u with respect to t. It's like we're getting at t through the intermediary of u. If t changes, then u changes, and if u changes, this whole quantity changes, and that's what we're interested in. What is that change compared to the change in time? And I'm being very verbose here because it's important to really understand what derivatives are. And I'm assuming some of you haven't quite gotten there, because I know in my own education, it was fairly late in the game where I really said, oh, aha, I really get what derivatives are. Still don't get how to pronounce them. Derivative. Okay. Well, as I said, the first thing we do is differentiate all of this with respect to u. Never mind the v, that's a constant. So it's really just f double prime of u, right? d du of f prime of u is f double prime of u. And then don't forget to multiply then by the derivative of u with respect to t. I've used the chain rule. But we've already established that du dt is negative v, right? If this is u, then when you take the derivative with respect to t, you get negative v. So there's another factor of negative v here. That factor with the first factor of negative v gives us this. So there it is. Let's rewrite this now using the more common notation, d squared f dt squared. This means the second derivative with respect to time of the height of the curve. Okay? Why have we done all this? Again, we're working towards this thing called the wave equation. So let's set that aside and look now at the derivatives with respect to position. Remember, the height of the curve depends on two things. Where are you? That's x. And at what time is it? Because as time goes on, obviously the curve changes. So what is the second derivative now with respect to position? Let's start with the first derivative of f with respect to x. And it's the same reasoning from before. Remember, f is really overall a function of this quantity u, the argument. If you change the overall number that you plug into the parentheses, you change the value of f. But the number that you plug in also depends on t. So the height of the curve really depends on time through the intermediary of this argument u. So we'll first differentiate with respect to u, and then take the derivative of u with respect to x. I'm using the chain rule for a function of two variables. Those variables are x and t. Now, how did I go from this to this? It's like I just got rid of du dx. Well, when we go down here now, we're doing the partial derivative of u with respect to x. That means freeze time. So you're watching this wave go by, stop the clock, the wave is frozen. You're not going to let time increase or decrease now. You're just going to scoot to the right or the left. If you're at a particular value of x, like x equals 7, now you're going to increase x just a little bit and ask, how does u change? So that's what du dx is. It's the ratio of those two changes, du compared to dx. Well, hopefully you can all tell that du dx, if you treat this as a constant, remember, when you do a partial derivative, the other variable you regard as just a number. du dx is merely 1. Right? d dx of x is just 1. And so this is really just the number 1 right here. That was easy. So now when it comes time to take the second derivative with respect to x, and this is not acceleration because this is not a time derivative. We're taking the derivative with respect to x of df dx. Well, df dx we just determined is f prime of u. And again, this function is a function of u. F is a function of u. When you differentiate it, you get some different function of u. So this depends on, this quantity in the brackets depends on u, but u depends on on x as well. That's the dependence that we're interested in. So let's use the chain rule once again. First, we'll ask, how does this quantity change with respect to u, and then multiply by du dx. Well, the derivative with respect to u of f prime of u is f double prime of u. And once again, for this specific case, du dx is just the number 1. I realize this is very long-winded. There's a lot of words coming at you, and you're just looking at some equations with several letters. Your eyes are probably glazing over. It's not going to be like this the entire semester. But if you can follow this, it will be satisfying when we next look at disturbances on actual strings, and we use Newton's second law to analyze the coupling between all the particles of that string. Okay, let's rewrite this as d squared f dx squared, and there it is. So we've now established the expressions for the second derivatives of the height of the curve with respect to position and with respect to time. I'll put those side by side. And do you notice the similarity here? These equations are the same, except for the fact that the second time derivative has a v squared in front. Pardon me. So evidently, f double prime of u is the same as the second derivative of f with respect to x. And that's a mistake, right? I should have a squared there. Let me fix that. Okay, much better. That was going to bother me. So since these two are the same, laser pointer please. Since these two are the same, we can over here replace f double prime of u with d squared f dx squared. And what do we get? Are you ready for it? Drum roll. Slide transition. Aha. This is the so-called wave equation in one dimension. It relates the second derivative with respect to time of the height of the curve to the second derivative of the height of the curve with respect to position. And since time derivatives, well, second time derivatives involve acceleration, what we've really done is relate the acceleration of a particular particle in the string, let's say, to the curvature of the profile of that string. Remember, first derivative with respect to position, that's the slope of the graph. Second derivative would give us the curvature. So that's kind of a nice way to think about it. We've related the acceleration of a particular particle in the string to the curvature of the string at that point. And we'll have more to say about that. I just want to see that transition one more time. Have you memorized it yet? At least be able to recognize it when you see it. Now, since we'll be looking primarily for now at waves on strings, let's switch now to the notation used by your book. So remember, x is like an index that specifies which particle you're talking about on the string. Now, of course, at a particular x coordinate, there's a bunch of particles there because a string isn't that thin. But let's just think of it like a sequence of individual atoms even, or molecules. So x specifies which of those particles you're talking about. And the displacement, capital D, again, can be written as a function of two variables. First of all, you have to specify which particle you're talking about. In other words, which position on the x-axis you're at, and how does the displacement depend on time. So instead of the letter F, we can move on to the letter D. We'll make that substitution, and that means we can rewrite the wave equation like this. This is how it's presented in your book. Once again, it says for any particular particle on the string, the vertical acceleration of that particle is proportional to the curvature of the string at that point. Isn't that a nice little GIF in the corner there? So the most important type of traveling wave that we'll talk about, the primordial, archetypal, quintessential, I'm running out of words here, traveling wave would be the sinusoidal wave. And there's no time to make a detour on this subject right now, but one reason sinusoidal waves are so important is that basically any traveling wave, no matter the shape, can be built up as a sum of sines and cosines. That's called Fourier analysis. So there's a reason for putting so much emphasis on sinusoidal waves. And in order to learn more about that, you'll have to take a more advanced class, but many of you, I guarantee it, will see that in the future. Okay, so going back just for a moment to our previous notation, if I could pause time, I can't pause time on this GIF, but at t equals 0, your wave disturbance has a particular shape. I was using the letter F for that so-called parent function, which we end up translating right or left. And let's let that original function be this one right here. Some amplitude times the cosine of this constant k is not the variable, times x. And now that it's, we're going to translate this to the right in this case, we replace x with the quantity x minus vt. So just take this quantity, which I was previously calling u, plug it in right here for x, and then you get this. And you should be convinced at this point. If not, go back and rewatch the video, and hopefully you're not bored out of your mind listening to it the second time, but hopefully you're convinced at this point that this does represent this shape translating to the right, exactly what you see here. Now, what's with the k? We're going to see that it's convenient to include that constant. Well, not only convenient, but necessary. So make sure you recognize it doesn't matter how many outer layers there are. I mean, what really is f of u? This is u. What is the sequence of operations that we label with the letter f? First, you take your quantity u, you multiply it by k, you take the cosine of that, and then you multiply that by the amplitude a. So there's 3 operations in this function. It doesn't matter how many operations there are, how many layers, successive layers there are, as long as your overall function has at the center of it x minus vt, you know that your function is describing a disturbance which travels to the right with speed v. Okay, so now we'll relabel this with a capital D to be consistent with your book. And what's our next step? How about we distribute the k within the brackets or within the argument of the cosine function? And we get this. Now this quantity kv is typically labeled with a new variable. It's really not new because we've looked at it already. Let's agree to call that omega. Again, not a w, it's that rounded looking w. Omega is defined as the product of kv. And honestly, until I prepared these slides, I hadn't memorized it in this form. I'm very familiar with this equation or this formula, which is of course identical. It would be convenient for you if you can memorize both of them, but have one of these at least just memorize so that you can easily convert from omega to v or from v to k. In other words, as long as you know 2 of those quantities, you can find the third, because you will encounter that problem many times this semester. So back over here, I will relabel kv as omega, and there it is. This is the function that you'll be most familiar with a month from now. That's the one you want to memorize above all others. And let's review the vocabulary here, the nomenclature or nomenclature, as I hear some people say. Capital A is for amplitude. We call k the wave number. And I'll point out right now, k is like a spatial frequency. We know that omega is an angular frequency that describes how quickly the wave oscillates in time. Well, k tells you how quickly it oscillates in space. So they're both kind of like frequencies, but this is a spatial frequency. We call it the wave number. And again, angular frequency and frequency technically are two different quantities. If you took this and divided by 2 pi, you would have what's called just frequency. More about that later. Lastly, you might want to shift your function left or right. So if you were at the origin, x equals 0, at t equals 0, when you're starting your clock, if at that position and time your cosine function had been shifted right or left, you would need this phase constant to make that happen mathematically. That's all the phase constant does, is shift the function right or left, which is why sometimes it's called the phase shift. Here we are back in the Desmos graphing calculator, and let's get some familiarity with the meaning of each of those terms. Amplitude A times the cosine of kx minus, again, I can't use Greek characters, so I'll go with the W for omega. And let's choose to make all 4 of those parameters. If we increase the amplitude, there's the obvious effect. Again, if this was representative of a light wave, increasing the amplitude would correspond to a brighter light, or in other words, a more intense light. Notice if I make the amplitude negative, that just inverts the function. What about changing the wave number k? I mentioned that the wave number is like a spatial frequency. So if I increase k and increase that spatial frequency, you might expect it to oscillate, quote, more quickly in space. Quickly really denotes a rate with respect to time, but because keep in mind, this horizontal axis right now is the x-axis. It's as if we've made waves on a string, we've frozen time, maybe just taken a picture with a high-speed camera, and this shows the variation of the displacement in space, not in time. Now, it so happens that if you look at a particular position on the string and watch how it moves up and down in time, it also moves sinusoidally. And that's a very confusing point for a lot of people when they first begin working with these wave functions. Whether you look at a graph of displacement versus time or position, they're both sinusoidal. Okay, so here I am increasing k, and sure enough, it's oscillating more times per meter, so to speak. Remember, the units of k are inverse meters. I say remember, but we actually haven't gotten to that yet. We will. What's happened to the wavelength as k goes up? Let me put k back to something like this. As I increase k, the wavelength gets shorter. And that's a relationship you just want to memorize. A higher wave number corresponds to a shorter wavelength. And that suggests a reciprocal relationship. And we'll see k and wavelength really are reciprocals. What about omega? Remember, W really is omega, Greek letter omega. Aha. So it appears that it's just translating the function right or left. And that's a little misleading because what it really means is as I increase omega, I'm increasing this quantity here. And we know that the bigger that number is, the further to the right the function gets translated. It'll be clearer what that means if we first look at what happens with t. So let me go back to a smaller value of omega. And I'll hit play on time. So here's our wave translating to the right. And what I'd like you to do is pick a particular point. The obvious choice would be the origin. Just look at the particle that hangs out near the origin and watch it oscillate up and down and try to conceptualize or try to see the time frequency of its oscillation. How quickly is it bouncing up and down? Again, so focus your attention on the point right here as it goes up and down while the wave passes through. It's kind of tough to do, isn't it? Because your eye tends to be caught up with the motion of the wave as a whole, when I'm really asking you to focus on that one point. Hopefully you're able to do that. So watch what happens when I now increase omega. So I'll hit play. See how much more quickly the point at the origin is going up and down? And of course, you can also see that the wave speed has increased as well. That's not surprising because remember, wave speed is omega over k. I don't have PowerPoint in front of me. Omega over k. So if omega goes up and k is the same, the speed also goes up. And of course, if the wave is traveling faster, then any point on the string will be oscillating up and down more quickly. So hopefully I've convinced you that for a fixed k, increasing omega means the wave speed goes up, and it also means that the time oscillation of each particle goes up, which is why we call omega the frequency, the time frequency. Do you remember what happens if we replace the minus sign with the plus sign? Ooh, what's that? That was strange. Yes, the wave, wait a minute. That's not doing what it's supposed to be doing. Oh, that's because my omega is a negative number, and a plus sign with a minus number actually would be a minus sign. So what did I just do? Let me restore omega to a positive value. And now I think we'll find that with a positive value for omega and a plus sign, this wave translates, as time increases, the wave translates to the left. Okay. A wave progressing to the left or a wave progressing to the right, hence the name progressive waves. Your book just calls them traveling waves. Here's a further bit of vocabulary. The distance between two successive peaks on the wave is called the wave length. So this is a graph of the disturbance in space, snapshot, as your book calls it. So you've taken a picture at a particular time. And we use the Greek letter lambda for wavelength. Almost everybody uses that letter. And of course, you could also just measure the distance from trough to trough. That's the same wavelength. Really, you could pick any two corresponding points on the wave. The wave is periodic. This would also be the wavelength. It's easiest to go from peak to peak or trough to trough. Delta phi, the Greek letter phi, this is the phase difference between these 2 points. You all have enough background in trigonometry to know what I'm talking about. Sine or cosine repeat every time the argument goes through 2 pi radians, or I could say every time the phase increases by 2 pi radians, right? Same as increasing by 360. So whatever this angle is, if I increase by 360 degrees, that brings me here. I've gone through 1 wavelength. So once again, going from peak to peak or trough to trough requires that the argument of sine or cosine increase by 2 pi radians, or I should say the phase increases by 2 pi. So delta phi is the phase difference. There's a particular phase associated with this point on the graph. Another phase is associated with this point, but the difference between those 2 numbers is what we call the phase difference. And you want to get to the point where it's easy to just visualize a half wavelength, a quarter wavelength. So from a trough to a peak, for instance, would be half the wavelength. And if a full wavelength is 2 pi radians, then the phase difference, delta phi, between those 2 points would be pi radians. That's another thing you just want to memorize. If you're at the trough of one of these waves and you advance by pi radians in phase, that brings you to one of the peaks. That will be useful to us later. And a quarter wavelength, you know, I like to refer to the shape of sine and cosine. This is 1 hump. So 1 hump has a phase difference of pi, 2 humps. So here's a hump above and a hump below. That would be a phase difference of 2 pi. Well, this is half a hump, right? We've gone from trough to 0. That's a half hump, which is a quarter wavelength. And that phase difference, I'm sure you can do this in your head, right? Would be pi over 2. And I have that memorized by just thinking of cosine. Cosine drops from 1 to 0 in pi over 2 radians. So I think you should memorize all those numbers if you don't have them memorized already. Okay, what's going on here? let this symbol x represent a particular coordinate on the x-axis. And what does this function tell us? This is the height, this number, after you plug in k, x, omega, and t, and a, the number that comes out of all of that represents the height of this curve right here at this position on the x-axis at that time. That's the meaning of this function. It gives the height of the curve. So what happens if we scoot over one wavelength at the same time? So time is frozen. If we scoot one wavelength to the right and plug that value of x in, what should be the height of the curve right there? So I've replaced x with the quantity x plus lambda, one wavelength to the right. Well, we know from just the definition of wavelength that the height of the curve right there is the same as it was here. Everybody see that? The height of the curve is the same when you just scoot over one wavelength. So the value of this function, or the value of the function at x plus lambda, should be the same as the value of the function at just x. In other words, they have to be equal. And what does that tell us? Well, let's just rearrange terms here. So I've distributed the k, and then we'll flip the order of these two. Let me flip those. And I've highlighted this quantity because that's the entire argument of the function on the left. So all we've really done is add this quantity k lambda. How are these supposed to be equal if we've got this extra term in the argument? Well, do you recall that, and this is true for sine and cosine, if you add 2 pi radians to the argument of cosine or subtract, you get the same value of the function right back. So this is an identity that you should know. It's true for sine and cosine, and also tangent, although tangent is the same even if you add pi, I believe. So evidently, this quantity is 2 pi. In order for the function to have the same output as it did before, this extra term would have to be 2 pi. Now you may be thinking, this is also true if you add 4 pi or 6 pi, etc. And that's true, but because we've only gone one wavelength to the right, we're adding 2 pi. The 4 pi shift would correspond to moving 2 wavelengths to the right. Okay, but the important takeaway is this quantity, k lambda, is 2 pi. You have to memorize that. If you have trouble memorizing things, put it on your note card for your exam. If you run out of room on your note card, consider getting a tattoo, because we can't punish you for that, right? If you have a tattooed on your arm, no, then you're going to get a fake tattoo. I take that back. Never mind. I suppose if you tattoo it on the back of your eyelids, we won't know about it. But the product of k and lambda is 2 pi. Let's look at that more carefully. 2 pi what? 2 pi radians. And technically the radian is unitless. If you've taken 3A with me, you definitely know that the radian is the ratio of one distance compared to another. So it's unitless. But we know that wavelength, it's in the word length, has units of meters in SI. And that implies that k must have units of inverse meters so that their product is unitless. That's a useful technique in physics. You can often infer the units of a quantity, but by looking at its role in a formula that you know. And this is consistent with what I said earlier. I described k as kind of like a spatial frequency. It's the number of times the wave wiggles per meter. There are the units per meter. So you want to memorize that. And of course, oops. Before I move on to that next point, let's revisit the transverse wave sim from the D. Russell page, and just focus your attention on one of these particles and the rate at which it's bouncing up and down. That is what we call the angular frequency. If you're just talking about the number of times per second that it wiggles, that's frequency. If you're talking about the number of radians the corresponding cosine function wiggles through, that would be called the angular frequency. And if the frequency were raised in this simulation, you would see each of these dots just wiggle up and down faster. That's all. We'll do something similar now with time. You have to shift your mindset here. This graph is now a plot of one of those dots' vertical position in time. Just pick one of the dots in that simulation and plot its vertical displacement in time. So this is now the t-axis, not the x-axis. This is not what your book calls a snapshot graph. This is what your book would call a history graph. And at this particular time, t, evidently the particle had a maximum oscillation, or a maximum displacement, I should say, upwards. And let's move one period to the right. So the period of the motion is the amount of time it takes to repeat in time. Each of these particles oscillates in a periodic fashion. And one period later, it's right back where it was. It's a lot like the wavelength. In fact, if you just look at the shape here, you know, when you're looking at this graph on a piece of paper, the history graph on a piece of paper, it is the wavelength, but we don't want to call it that because that will confuse us. Wavelength is the distance between peaks on a graph of displacement versus position. Right now, we're looking at a graph of a particular particle's displacement in time. And so we really need to call the peak to peak distance, it's really a time interval called the period. So we'll use capital T for period. And just like before, if we take our function, after you plug in the wave number, a particular coordinate on the axis, the frequency, and a particular time, that tells you the height of the curve. And we know that one period later, if you plug in t plus 1 period, the height of the curve is the same. So the two functions should have the same value, or I should say the functions should have the same value at those two times. Let's rearrange. So distribute the omega. This minus sign here makes that a minus sign. And since this is the same as that, cosine repeats every 2 pi radians, evidently. And like I said, it doesn't matter if you add 2 pi radians or subtract 2 pi radians. This quantity right here would have to be equal to 2 pi. It's a lot like kx equals 2 pi, but now we're relating the frequency to the period. As far as dimensional analysis, we know 2 pi is unitless, but period is a unit of time. It's got units of seconds, and hence the angular frequency must have units of inverse seconds. Makes sense, because what does omega tell you? It tells you how quickly the particle wiggles in time. In other words, how many radians it wiggles through per second. There it is, per second. So if you put those side by side, maybe that'll make it easier for you to remember them. You must remember these. You don't want to have to be looking this up in your book every time you do a homework problem. You certainly don't want to have to be looking it up on your note card during your exam 1 problems. You just want to have this memorized. So K is the reciprocal of wavelength with the factor of 2 pi in there, and omega is the reciprocal of 2 pi. The longer it takes something to oscillate, so the longer the period, the lower the frequency. You could even use, for instance, the orbital period of the moon. You know, the moon goes around something like once a month. So the period would be about 28 days. The frequency is the reciprocal of 28 days, which in seconds is a really small number. Definitely memorize these two formulas. Okay, so we'll take those two relationships, those reciprocal relationships, and plug them back in just to see a different way of writing this familiar function. This is the way we're going to write it most often. But for some problems in your homework, for example, you may see it written a slightly different way. K is the reciprocal of lambda. This is the wave number. Here's the angular frequency written in terms of the period. And since they both have a 2 pi, we can factor that out and write it this way. And I didn't include this as a slide, but when you write it this way, it makes it obvious why increasing the position by 1 wavelength doesn't change the value of the function. Because check this out. If you change the numerator here from x to x plus lambda, just imagine a plus lambda right here. Lambda over lambda is 1. 1 times 2 pi is 2 pi. You've added 2 pi to the argument inside the brackets. That's not going to change the value of the function. So writing it this way hopefully makes it obvious why shifting by 1 wavelength in space or shifting by 1 period in time does not change the value of the function. You're just advancing the overall phase by 2 pi radians when you do that. So compare and contrast. I remember that from busy work in elementary school or high school. What's the difference between those two? Contrast, compare? Doesn't that kind of mean the same thing? Compare that to the first way that I wrote it, because I began by emphasizing that this is a function at its core of u, x minus vt. I was calling that u. But we've seen that that is equivalent to writing it this way. So just as a quick review, can we confirm that these are the same? Well, if that's true, if these are the same, look at the coefficient of t. See how we have a k times v? So kv is the coefficient of t. But here, the coefficient of t is 2 pi over big T. See that? 2 pi over period. So if these functions really are the same, then these two would have to be equal. Does that make sense? Well, remember, 2 pi over the period is omega. So we've really just confirmed our previous formula for the relationship between omega, k, and v. Again, if you can memorize that, that will help you. The last thing we should do here is check whether our sinusoidal progressive wave does indeed satisfy the wave equation. We know it should, because we've already established that any function of x minus vt will satisfy the wave equation. But let's just double check that it satisfies this equation. Of course, we're going to call it capital D of xt. So we'll start with the first time derivative. Take the function up here. Hang on, my toolbar's in the way. The first derivative with respect to time. Well, we know that the cosine turns into a negative sign, but the chain rule requires us to take the derivative of the inside with respect to t. Remember, this is a partial derivative. So right now we just pretend that x is a number. It's just a constant. So when we differentiate with respect to t, we pick up this factor negative omega. Well, the minus sign from negative omega cancels the minus sign from turning cosine into negative sign, and so we're left with this. Let's now take the second time derivative. What's the time derivative of this function? Well, now sine turns into cosine, and we pull out another factor of negative omega, and we're left with this. And let's check something. I've been pointing out that the second time derivative of d, that's really the vertical acceleration of a point on the string. And we know that acceleration has units of meters per second per second. Do we have those units on the right side? Obviously, we can't compare apples to oranges. We must have the same dimensions on both sides. Well, omega has units of per second, inverse second. So we've got inverse second squared times amplitude, which is a length. And we do, in fact, have meters per second per second. Okay, that's the left side of the wave equation. Now let's check the right side. We're going to need the second derivative with respect to position. So we go up here. Again, cosine turns into negative sine. And then since we're differentiating with respect to x, we now pretend that t is just a number. We're asking how the function changes when x changes. Chain rule tells us that we pull out a factor of k. So we have a negative sign and a k out front. Let's now take the derivative of this to get the second derivative with respect to position. The sine turns into a cosine. We pull out another factor of k, and we're left with this. Okay. Can we confirm that the second time derivative is v squared times the second space derivative? Well, let's recognize that omega squared, remember, omega is kv. So if we square that, we can rewrite omega squared as k squared v squared. And let's now compare this line to this line. See my courtesy blue boxes there to help you see that? Evidently, the right side here is equal to the right side here after you multiply by v squared. The only difference between the right sides of these equations is the presence of that v squared. So I've now shown that the second time derivative of the displacement is the square of the speed, there's that extra term, times the second space derivative. And voila, there it is. We've shown that these progressive waves do indeed satisfy the wave equation. And we'll be using them quite a bit in the next several chapters. Okay, we're finally done with this video. Remember, you can always pause, right? And I also want to say, I'm being really pedantic here and describing in detail some things that many of you probably already know. Maybe you've known some of this stuff since high school and you never forgot it. And so you're thinking this is moving really slow, but it will pick up. We will be looking at material with which you're unfamiliar. So don't be lulled into a false sense of complacency. Till next time.